Good evening, students. Today's session we are going to explore the optimal control system following a nonlinear systems. Okay, so the type of controller which you can propose for the nonlinear system, one of the type of the controller which can be proposed for a nonlinear system is an optimal control system. Let us see what is an optimal control system. Okay, so optimal is a Okay, so coming to what is an optimal control system. Okay, so optimal control system is nothing but to maximize the output for a minimum cost. Okay, so here they represent maximize the return from the system. Return from system is nothing but the output for a minimum cost. Okay, so in other words, you can the optimal control problem is to find the control which causes a system, that is x dot is equal to g into x of t comma u of t comma chi. Okay, so this is a system. Okay, so the objective is to follow the optimal trajectory that minimizes the performance criterion. Okay, or you can say this as a objective function j is equal to, it's a function of h of x of t comma u of t comma t into dt. Okay, and next. Okay, so mathematically speaking, it is possible to write the most optimization problem as minimize the objective function subject to a constraint, and this is a design vector. Okay, so the objective function is represented as f of x, and subject to a constraint h of x equal to 0, g of x less than or equal to 0, and this is a function of design vector. Okay, in other words, you can say maximize y is equal to f of x1 comma x2, where x1 x2 are design variables subject to a constraints f1 is f1 of x1 comma x2 less than or equal to 0, and f2 of x1 comma x2 less than or equal to 0. This is another one. Other words, you can even define this as a vector of design input data, objective function, and set of constraint functions. Okay, so now there are five types of optimal control problems. Optimal control problem is mainly used in aircraft flight control system. So first one is a terminal control problem, next is a minimum time control problem, next is a minimum energy, then followed by regulator control problem and tracking control problem. Coming to the terminal control problem, it is mainly used in flight control system. It is used to bring the system as close as possible to a given terminal state within a given period of time. Okay, so example is automatic aircraft landing system, where the optimal control policy will focus on minimize the error in the state vector at the point of landing. And similarly, minimum time control problem. So you have to reach the terminal state in a shortest possible time period. Okay, so this is in case of a car journey. The driver always keep his foot in the accelerator for entire journey except at the terminal point in where he brakes as early as possible. That is minimum time control problem. And next is minimum energy problem. So if you take a satellite control, it is always required to have a energy to transfer the system from initial state to final state with a minimum expenditure of control energy. Okay, that is called minimum energy problem. And regulator control problem. Regulator control problem is when system initially displaced from equilibrium, it will return to a system to the equilibrium state in such a manner so as to minimize a given performance criteria index. And next one, last one is a tracking control problem. This is used to cause a state of system to track as close as possible some desired state trajectory in manner so as to minimize the given performance index. Okay, and coming to the performance indices, it depends on the nature of control problem. Okay, so for example, design of autopilot of racing yacht, so regulator problem, classical control design techniques, optimal control design techniques. Okay, so selection of performance criteria, so you have to minimize the distance of track, minimize the heading error, minimize the rudder activity, and minimize the forward speed loss. Okay, coming to the quadratic performance indices, so you represent the index as j is equal to qx plus r into u into dt. Okay, so this is a quadratic performance indexes. Okay, so here you represent the control law as u is equal to minus k into x. Okay, the same objective function can be represented as q11 x1 square plus q22 x2 square plus q33 x3 square plus r1 into u square into dt. Okay, so or else you can represent as x transpose qx plus u transpose ru into dt. Okay, so this is a state of the system, and this is a control vector x is equal to u is equal to minus kx, followed by your output y is equal to c into x. Okay, so the linear quadratic regulator, that is LQR, it provides the optimal control for a linear system with a performance index. Okay, so here you have to choose a performance index as j. Okay, so and that j should be, you have to represent that as a function of t. Okay, and just integrate that with respect to t, and you will get x transpose px. That is a relationship. Okay, so here finally it belongs to the class of nonlinear differential equation. So p dot is equal to minus pa minus a transpose p minus q plus p b r inverse b transpose into p. Okay, so finally you will get what is P dot? That is a continuous solution of matrix Riccati equation. Thank you, students.